the last speaker in the last session, he's newly arrived, and the next 5 speakers are also newly arrived. In fact, 3 of them haven't even arrived yet. But they came for this so that they could tell you what they're doing and try to get you interested in their research. So we're going to start with a couple talks on astronomy by Adam Bolton and Innes Ivans, and then 2 biophysicists, and then a new kinetic matter physicist, and then we'll end the session with Brian Somm, who's been here a long time, but I didn't know where else to put him. So here we go. Go ahead and take it away.
Okay, how do I get my, not my
Oh, it's just
mug shot or my, oh, you just okay, great, so I'll get going on my time, obviously. So I mean this title in both senses, sort of with the parenthetical statement included and excluded. Everything I'm going to talk to you about is work that's done in the context of the Sloan Digital Sky Survey and now the Sloan Digital Sky Survey Part 3, which is a large multi-institution collaboration, hundreds of people. University of Utah is a full institutional partner. And yet the work that I'll talk to you about is sort of in some sense, a niche within that collaboration that involves a much smaller number of people, and it's somewhat more intimate. And yet out of that comes a lot of really interesting stuff that's had a really significant impact, even beyond the Sloan survey, in areas that it wasn't really intended to impact when it was originally designed. So I'll launch right in here. So this all begins with the SDSS 2.5-meter telescope. This is in Apache Point, New Mexico, not terribly far from here. 2.5-meter diameter primary mirror. Not one of the biggest telescopes out there, but not one of the smallest either. And in particular, what it lacks in aperture, it makes up is a field of view. This is just a shot of the primary mirror looking down the tube there. That thing protects the telescope from wind and other sorts of things. Just a little schematic diagram of the telescope itself. One aspect of the telescope is this very large digital camera. It has a 3-degree field of view on the sky. It takes pictures in multiple colors of galaxies and stars and quasars and whatever else happens to be out there. It takes it through these various photometric filters, which are what we use to reconstruct the approximate colors of the things that we're looking at out there in the sky. So here's a typical Sloan Digital Sky Survey picture. To give you a sense of scale, this is 20 arc minutes here. The full moon is about 30 arc minutes in diameter, so the size of the full moon would be about like that. And we're just going to zoom in on this picture here, and you'll be able to see some of these points of light in a little bit more detail. You can see funny little artifacts. Real data has funny things that look like this, stars and missing filter information, but just ignore that. And we'll zoom in here. You'll see some of these boxes, some of these things have been highlighted with red boxes now. And I'll tell you what the point of those red boxes are. Actually, is it possible to get the light down a little more without being completely off?
How's that?
Yeah, that's, I think, a little better. So we can see we're zooming in right now on this particular little smudge in the center here that has sort of an orangish color to it. And this is a luminous red galaxy, a giant elliptical galaxy. It's one of the largest galaxies in the universe, or I should say it's a member of the population that collectively represents the largest, the most massive galaxies in the universe. And what we do with these, all of these objects that you see on here that have little red boxes around them, which you may not be able to see, is we actually take the camera off the back of the telescope and we put on this funny contraption that has an aluminum plate, and there are little holes drilled in the plate at the positions of those objects, stars, galaxies, quasars, what have you. And when this thing goes on the back of the telescope, most of the light just hits the aluminum plate and is lost. But at the positions of these holes, the light goes into these optical fibers, and it gets fed through those optical fibers to a spectrograph, which is represented here just in terms of a schematic diagram, not an actual picture of the spectrograph. The light gets dispersed in wavelength, and we can actually see the detailed distribution of light from these objects in wavelength. And this gives us information not just on their 2-dimensional positions on the sky, but 3-dimensional information as well. And galaxies that look like this have spectra that look like this. Galaxies that look like this have spectra that look like that. And in particular, from these detailed features here, we call them lines, emission lines, or absorption lines, we can tell the cosmological Doppler shift of these galaxies, and we can tell essentially how far away they are along the line of sight. So this is how we map galaxies, not just in 2 dimensions, but in 3 dimensions. And this is the sort of the primary mission of the Sloan survey is to make maps just like this. This is a slice through the Sloan survey, and you can see large-scale structure and the distribution of galaxies that we can resolve by mapping them in 3 dimensions. But what I'm going to talk to you about actually isn't that main project, it's this side project. Well, it's a side project to the survey, but it's a very main project to me. This is the spectrum here. The data is shown in white, and there are 2 components that you can see in the spectrum. There's this absorption line component, which accounts for most of the light. That's from one galaxy at a redshift, which is to say a sort of a distance proxy of 0.32. But then there are some emission features from a much more faint galaxy at a redshift of 0.6 or so. And that tells us we have 2 galaxies in one spectrum. Well, what can happen when you have 2 galaxies along the same line of sight is that the gravity of the more nearby object can actually deflect the paths of light from the more distant one, and these divergent paths become convergent paths, and we can actually see multiple images of the same object. And the angular scale of this effect gives you a measurement of the mass of the foreground galaxy, a much more accurate measurement than you can get through any other means. And that's what makes this not just a neat trick, but an actually pretty powerful scientific tool. These are just some toy models of things that you can see. If you have perfect circular symmetry and alignment, you get this ring. We call it an Einstein ring. There are various ways of tweaking the symmetry to get doubles or quads or funny multiple combinations here. I'll just move on, but with those collections of what we call lens candidates that we get from those spectra, we then propose for time on the Hubble Space Telescope, which has much better image resolution than the Sloan telescope, and we can actually resolve these things into the foreground galaxy, which you see in the center in this kind of orange color, and the Einstein ring images of the background galaxies, which you see in blue around the outside. And just to show you what the difference between the Sloan data and the Hubble data, this is why we really need to go to space for this. You just can't measure these sorts of angular scales without space-based observations. This is about 2 arc seconds on a side. There are 3,600 arc seconds to a degree. So that tells you the small scale that we're working on here. But we don't want just pretty pictures. We actually want to get some numbers out of these things. So we have to do things like mask out the cosmic rays. We also detect cosmic rays, although to us they're noise, not signal. So we have to mask them out and subtract the image of the foreground galaxy, and then construct a mathematical model for the gravitational field and the mass distribution of the foreground galaxy. And I'll just illustrate that here. This is a sort of a nonlinear optimization process whereby we model these Einstein ring images, and the parameters of that model become the mass measurements for the lensing galaxies. So what do we learn from that? We learn a lot of things. Some of the most significant results to come out of this are the result that massive elliptical galaxies have a universal mass density structure that doesn't change with mass, but they have a systematically increasing fraction of dark matter as you go to higher mass galaxies. There are certainly many more of these quantitative plots that I can show you, but I'll show you some of the pretty picture plots instead. These are somewhat hyper-realistic in their color scheme. I can go into that in more detail if you want, so don't take the colors at face value, but essentially on the left side here, these are data, and these are the models that we use to represent that data, to reproduce it, and to extract the mass parameters of the lensing galaxies. All of these images are about 6 arc seconds on the side, so very small. This is all Hubble Space Telescope data and models. So now what do? The original Sloan survey has completed its run, and the telescope has been upgraded with a new spectrograph. And a survey is just getting underway now, known as the Baryon Oscillation Spectroscopic Survey, or BOSS. This is a shot of one of the BOSS cartridges. You can see it's more densely populated with fibers. There are 1,000 fibers per plate instead of 640. The spectrograph has also been upgraded. And what is that going to get us in terms of strong lensing? Well, it's going to let us go to higher redshift, which is to say greater distance. We'll look at younger galaxies, massive elliptical galaxies, back to when the universe was half its current age. And by combining these 2 samples together, we'll be able to get an understanding of the evolution of mass structure and of the dynamical structure of these massive elliptical galaxies. And that's just getting started now, so that's what I'm thinking about, that's what I'm working on. So that's the, I guess you need some guts to go with the glory as well. Here's the, a lot of the work is involved is cultivating what I would call a healthy obsession with the finer points of CCD pixel level spectroscopic data analysis. I won't try and tell you what this picture is here. I can tell you about that, or you can read about it in the paper. This is images from the BOSS spectrograph. On hand, they have to take these noisy two-dimensional spectrographic images. Again, we have cosmic rays here, so we're also a cosmic ray group. But we have to get rid of those, and we somehow have to reconstruct the one-dimensional spectra of the galaxies and quasars from these messy-looking sorts of exposures like that, and that's still ongoing work as well. Anyway, if any of this sounds interesting to you, and if you're not afraid of writing computer code, certainly come talk to me, or send me an email, or track me down any other a number of ways. All right, thank you.
Thank you, Adam. So any questions for Adam?
So do you do the modeling that you're showing, that's what you focus on?
That's one of the things. Yeah, that's not certainly not the only thing, but it's yeah, it's one of the projects that would you could definitely focus on it as a thesis type project.
Some other hand over here.
Why the pool stick?
Why the pool stick? It transmits vibration less than a laser pointer, so it makes me seem more cool-handed than everything.
Okay, thank you, Adam. So now we have Ines, who is also working in astronomy, and I think even using some of the same tools, same telescopes.
Yes, as well as others. I really enjoy going observing, and this is one reason why some of you who otherwise would have seen me around but haven't seen me very much this fall. I'm traveling to Chile using the Magellan telescopes at Las Campanas. Most of what I do does use ground-based observations, although Hubble Space Telescope obviously delivers data right to your desktop. Sloan Digital Sky Survey, Adam made a very nice intro to that, thank you very much, will provide data of the sort that he described for objects that you call up at will. So it's observed millions of objects. It's observed over a quarter of the sky now. It's the largest astronomical survey ever attempted, let alone accomplished. And right now it's in phase 3, so it's divided into 4 basic working group areas. Adam and Kyle are working in one area called BOSS. I'm working in another 2. Segway is the Sloan extension for galactic understanding and exploration. And then there's Apogee, which is the Apache Point Observatory's galactic evolution experiment. One has been underway for some time now. It's in phase 2 of operations. There's megawatts of data. I'll show you a couple of images shortly. Apogee is just starting off the ground right now. It's a good time to start thinking about getting involved in that. If this sort of description of what I work on interests you, Apogee spectrograph is just starting to be built. It's got a 3-year survey life to end in 2014, so it's definitely on a grad student timescale. And I can talk more about that with anyone who's interested in perhaps becoming an architect for one of the next biggest surveys of the universe. I've got a lot of data in hand, and I've got a lot of projects that I'm working on. Some of them are PhD sized in scope. I would expect a student to eventually take charge, run with it. I also have smaller scale projects with more self-contained data set. There's still a publishable goal in mind, put out a paper, but they're smaller in scope. So it gives you a chance to try this on your size, see if you like it or not before you go on to do something bigger. Listing the people that I want to work with in 2 groups is just to remind you that in addition to this collaborative nature that I want to work on with people on projects, is an acknowledgement that some of you here are going to be more passionate about someone else's science than mine. But you may not have the RA that you like, or that you don't want a TA. I would still be very happy to work with you. I need people that are happy to work on data, like Adam. If you know computing, if you work with RF, IBL, Python, all those tools are definitely make you marketable and very helpful in the kinds of work that I'm doing. What I'm interested in most is applying high-resolution spectroscopic techniques of individual stars that belong to various stellar populations, deriving their chemical compositions, and using that information to sleuth out what happened before the stars that I observed were born. So I'm very interested in the idea of galactic archaeology, stellar alchemy, but of course, all of this touches on the origin of the elements, genesis, nuclear physics, nuclear astrophysics. You wind up working with people who run atomic physics labs in Wisconsin, nuclear physics labs in Germany, theoretical nuclear physicists in Italy. Observers will wind up traveling to all the telescopes around the world, whether they're in Australia, Chile, or Arizona, New Mexico. I would expect people who are going to be doing research in this area to go observing at least once, to not just rely on what data you can get through Sloan Digital Sky Survey or through HST, but actually go and learn the mechanics of observing on site. So this sort of lists the kinds of things that I'm interested in, the kinds of activities that I would like to work with other people here on. And so for the rest of the time that I have, I just wanted to give an illustrative example of one project that I'm particularly excited about right now. It involves following up on discoveries made in the Sloan Digital Sky Survey. What you're looking at here is kind of a map of about 20% of the sky. So this is the extent of what Sloan Digital Sky Survey has been able to observe so far. It's about 1/4 of the sky. The coordinate system in astronomy is in right ascension, going around the way longitude does around Earth. So it's a 360-degree coordinate system, usually divided into 24 hours. And in declination, we start at 0 in the equator, go up 90 degrees to the North Pole, south 90 degrees to the South Pole. So you see here, you're looking at from 0 to 60 degrees, and then the rest of this makes up the 1/4 of the sky. The color coding in this imaging is not the actual colors of the stars. What the folks here did was color code by distance. So they have estimated distances to the objects they observed, and here the blue things are closest to us, the red are furthest. You can see that there are streams of debris. There's actually a galaxy enmeshed in our Milky Way. It's on the other side of the center of the galaxy from us, so it wasn't discovered until about 10, 15 years ago. Sagittarius. We mapped it out, and it turns out it's leaving trails of stellar debris all around the sky. This is one of the things that I'm studying. Other things in this map show you globular clusters. These are objects that contain some millions of stars apiece. Milky Way has about 150 of these objects. They're fantastic at tracing out everything from dark matter distribution to actual individual nuclear synthesis and stellar evolutionary events. There's also a stream. When the press release came out for this in the late 1890s, I think, or early 2000s, they talked about a ghostly stream that they discovered around the Milky Way. They're talking about this entity here, this monster stream. We still don't know its origins. Another globular cluster out here used to be known as the intergalactic wanderer. It was the most distant globular cluster that we had found in our galaxy. Now these are pictures of globular clusters. You can sort of understand how they got their name. They're just globs of stars. There's millions of stars concentrated in a very small area. But one of the most exciting results that's come out of Sloan is we've discovered a near classic galaxy right in the halo of our Milky Way. These are the ultra-faint galaxies. We discovered them only because Sloan has so much data you can compare these to the globular clusters you just saw. You can just barely make out that there's an overdensity of stars in those images. They're really hard to find. What I'm interested in is finding out how they were made. Do they represent primordial galaxies out of which the galaxy was made? Were they made in some of these merger events with other galaxies? Are they just still, are they relics of more recent things? And so I've been going out to Magellan mostly. This is a picture of McDonald in West Texas, getting data of two-dimensional cross-dispersed spectra. So many of you are used to looking at 1D spectra, a range of colors distributed by wavelength. In cross-dispersed spectrum, it's sort of what it sounds like. They disperse the light and then cross-disperse it. So you can think of that spectrum as being dispersed for many, many yards or even miles and then chopped up and then put together in this format. Of course, these absorption features are what I'm interested in, and this is an image of a chip that I would be working with. And like Adam, anybody who works with CCDs in any lab is going to have problems trying to reduce the data so you're uncovering what object it is that you're studying and not the way in which you studied it. So there's an frequency cosmic rays, there's a bad column of data, there's this Narcissus effect in this particular spectrograph, there's an over reflection going on. These need to be reduced out of the data. And once you've done that, you get a one-dimensional spectrum that shows some continuum and some very deep features and some individual features. And then through some clever code, that's legacy code, it's based on quantum mechanics to the level that I needed, it was written in 1964, you can turn the data into abundances. So the strength of any absorption line is going to be a function of the parameters of the star itself, the temperature, the density, the radiation field, the number of absorbers. Well, we just employ the inverse operation. To get the abundance of a particular element, the number of absorbers between us and where the light is coming from, we can model the temperature, density, radiation field, and put in a measurement from the data of the absorption line and get out an abundance. And so this is our basic measurement. This is not the end of the study. This is now things get interesting. Once you've got the chemical composition of a star, here it's the sun, we're showing it basically the logarithmic abundances of the elements versus the atomic mass of the element. And so you've got a lot of hydrogen and helium in the sun, you've got a lot of the alpha elements, magnesium, silicon, the like, some iron peak, and then you get into the rare earths and there's much, much less. But then they're past lead and bismuth, you have a gap and you finally get to things that are radioactive but on very long time scales, thorium and uranium. So they're semi-stable. But here's where the interesting part comes in. Once you've got the chemical composition of the star, then you start inferring its history. You know where certain elements come from. Silicon, calcium, titanium mostly come from supernova, the type that are produced in extremely massive stars. Your iron peak elements come from supernova of a smaller mass that came into play in the galactic budget of abundances much later times. You've got rapid and slow neutron capture nucleosynthesis processes that you can investigate. And one of the things that I'm most interested in applying right now to one of these ultra-faint galaxies is a concept called nucleocosmochronology. A lot of syllables, but it's easy to parse it out. Nucleo. So it's something to do with nucleosynthesis. Cosmo. You know, it's astronomical. Chronology. Something about time. So what I'm doing is in one of these ultra-faint galaxies, there is a wealth of material that we can ascribe to have been produced in massive supernova through a rapid neutron capture process that required a large number of neutrons, a large amount of energy. When you have this process going on at a really big rate, you can also produce enough of some of these radioactive elements, uranium and thorium, in amounts that you can actually observe in stars. So this is a thorium feature. It's about 20% line depth down from the continuum, And you can model it very easily with very tight error bars. And for this star, we've got an age of roughly 12.5 gigayears. Those of you who have followed other estimates of the age of the universe know that this is one of the oldest star systems ever been found. The age of the universe being roughly 13.1, 13.5 gigayears, depending on which version of the results from the Wilkinson microwave and exotic control WMAP. Another example would be a much harder analysis. This would be uranium. You can see it's buried in a thicket of cyanogen. It's on the wing of an iron mine. It's already suppressed from the continuum. So you're trying to measure the age of this star based on very little information. But if you've got enough good data, you can do it. So these are the kinds of things that interest me, is taking chemical compositions of stars, applying them to learn something about the history of the stellar population in which they were born, which in turn can tell us something about the history of the origin of the elements, or how stars form objects such as the Milky Way or galaxies. So I'm looking for folks who want to do this kind of research, or at least would be happy to get an RA working with the data itself. And I welcome you to come by, talk to me, email me, phone me. I'm one of the new folks up in the fourth floor of SCC. And I thank you for your attention.
Thank you, Ernest. Any quick questions for Ernest? Okay, great, thank you. All right, so let's move on to Savisa Farian. So another new faculty member, biophysicist. 2 new biophysicists coming this year in January. So Savisa is the first one to talk. Okay?
All right, well, thank you very much for coming in this Saturday morning. And I would like to introduce Michael Rishinin.
Sorry.
Let's see if he can say it.
Sorry, oops.
Nice.
Thanks for that.
Okay, so I would like to kind of introduce, well, my lab doesn't exist yet, okay? So if you want, you can ask Harold to open up B23 for you and you're going to see an empty box. That's the lab. But what we're going to be interested in is going to be a question that has been of my interest for a while now. And that is, how do envelope viruses come out of cells? So we call it the dynamics of envelope virus budding. What you see here is this inside of this cartoon is the cell. You see a membrane, and this poor guy has been infected with this virus is HIV, has been infected with HIV, and you can see the membrane of the cell basically being taken away by viruses that are created from it. So you can see that the virus particle is starting here, then it comes out, it becomes like this, and eventually it becomes a virus that is very nicely, it has a lot of symmetry, it has a lot of packing, and it basically takes away part of the membrane of the cell. Eventually it kills the cell completely. We are interested. So these viruses that do this, that come out of the cell membranes and take a part of the membrane with them, are called envelope viruses. So our lab is going to be focusing on the mechanism by which these guys are born. Okay? So what is the driving force? What are the structural components under that? So we are going to start with a virus that's very simple. It's a horse virus called VSV, vesicular stomatitis virus. It has a very peculiar shape. This is an electron microscopy picture of it, and you can see it's a bullet-shaped virus. They are called the rhabdoviruses just because of that, because they look like bullets. This is an envelope virus. It's about 100 nanometers wide and 200 nanometers long. What you see on it, you see, this is like a brief anatomy of what goes in it. The first thing that you notice is that it's extremely packed. Okay? So this guy is completely packed with protein and DNA. On top of the surface, it's taking the membrane of the cell that it came out of, but it has all these glycoproteins. So these are special proteins that the virus needs to re-enter the other cell. So once the virus is released, it's going to use these particular proteins to actually come in and infect the secondary cell that it's going to get in touch with. These are extremely important for the virus to pack up with itself. Now, how does the virus know how many of these things to pack? It would actually pack a virus to pack up about 1,800 copies of the G protein. Okay? So it's very closely packed on the surface. Then inside the virus, you have a piece of RNA. Now, this is a very simple virus. We like to work with this because we can do all the biology of this virus ourselves. This has only one piece of RNA. So all the genetic materials of this virus is encoded in this one long polymer RNA. And you can see that the virus protects it very well. So it has proteins that bind it, compact it, and package it into this thing. And it has also, since it's a negative sense RNA, it has to have the reading machinery for this genetic actually packed into there too. So how does a structure so organized come out of a cell and pack itself in such a great symmetry? This is a picture, a model like Jordan showed, kind of a hand waving of what we think is happening. So we think that we know that the G proteins are pumped onto the membrane. The RNA is loose in the cytosol, and this is basically the genome of the virus. Somehow, this guy gets in touch with these and polymerizes itself into a closely packed thing, and then it has to also cut itself loose from the membrane. So for doing that, it needs to recruit a lot of cellular machinery that is involved in other aspects of the cell. So what we are going to be doing in the lab is we are going to be using this virus and viruses similar to this to observe this process in living cells and basically understand the kinetics, organization, and the whole process of the virus formation. Now, as soon as we want to do that, we hit a roadblock because these things are small. Okay, so this is a virus, it's diffraction limited, it's 100 nanometer size, and what happens if you put it in front of a lens? Well, a single point on this virus is going to give you a point spread function that with our microscopy it's going to be 500 nanometers long in the axial direction, 250 nanometers long in the XY, and so you have to deal with this. And we have mechanisms to deal with this. One of them I'm going to highlight is basically taking each color or each molecule at a time and imaging them separately so that each point spread function that you image, you can now find the center of the point spread function very accurately because you're bringing a priori information. You're saying, I know that there was just one molecule or one group of molecules, so what is the center of mass position of this one group of molecules? And then you bring the second group of molecules, okay? And you do the same thing, and you break the diffraction limit basically by looking at these two precise measurements. So we're going to be using tricks like this and tricks that you're going to cook up if you join the lab to basically look at how this virus is created. This is a movie I'm showing you. So that what tools do we have? The lab is going to be both in biology and physics. We would have ultimate control on the virus. We can modify the virus. We can put fluorescent proteins anywhere we like. So if this is the VSV, in this experiment, we have taken the P protein, which is a protein that's close to the RNA, and we have tagged it with fluorescent protein in red. And we have also tagged the G protein with fluorescent protein that was green. And what you see here is the touchdown of the RNA on the plasma membrane and creation of the virus. And what I would like to draw your attention to here is that when the virus is created at the bottom of the cell, you can see it being asymmetric. You can see it being a rhabdovirus, which is longer than it is wide, and it's going to start pivoting. Okay? So the virus is being created. So this is the kind of data you're going to be looking at. You will need to know all the information, as our astrophysics fellows also said, about your digital cameras, about the acquisitions. You need to be able to get information out of these fluorescence images and find out the mechanism by which this virus was created. So you see there is basically the point. So how are we going to do this? So since I knew that people are going to show telescopes, I thought that we were going to show a microscope. This is going to be our microscope. This is a new design of a microscope, which is basically a a microscope in a box. It doesn't have eyepieces or anything. It's designed to basically be your detection, be as close as possible to your sample, which you're going to put here. This whole microscope is going to be in an incubation chamber held at 37 degrees. It has these mirrors. It has 2 scanning mirrors here and 1 galvo mirror here that will basically allow you ultimate control of positioning of your laser beam and scanning for as the virus is budding and as you're looking at the cell. It will be fully automatic, and so you can access this microscope at different levels. You can do high-level programming. You can do programming like in C# that you have ultimate control on how you want to design your experiment and what kind of information you want to get. And eventually, we're going to like to move out of the VSV system and start looking at more, important pathogens like HIV and flu. And the reason why we don't start with HIV, at least not immediately, is because HIV is a little more complicated. I told you that the VSV has a single genome. HIV has 2, so it has to pack 2 pieces of RNA. So it's a little bit more difficult to work with in terms of the genetics. And flu has 8 pieces of RNA. Okay, so it's a little more complex in terms of biology, but all these viruses can be made safe and can be working in the lab. So at this, I'm going to stop and thank you very much for your attention.
Okay, any questions for Sadiq? Anybody worried about working with viruses? He addressed that, but you should you should be aware that we're doing this, that they're doing these in a very safe way. Any questions? Okay, so let's move on to Michael. Okay.
Hi. Well, I've already been introduced, but anyways, my name is Michael Bershin. I'm also a new guy here, and I'm also interested in biophysics. But what I'm interested in is how things move inside of cells. Okay, so transport is one of the crucial things for almost any living system, and that's what makes it so exciting and so interesting. And basically, if you think high level, just think of a city or a nation or something, it's really important to be able to move cargoes around so they get to the store, you can go there, buy it, bring it home, you go to work, you go back to your home, you go have fun, whatever. Motion is what enables all of these processes. Now, there's a lot of stuff happening while you're at work, hopefully, but you need to be able to get it. It's an enabling technology. And so by studying it, you also gain an insight into the structure of whatever it is you're looking at and what actually happens. If you know about a society, who goes where and what goes where, you know a lot to begin with about a society. So it gives us a window on understanding how the cell works. And a lot of biology, especially now that it's getting more and more quantitative, is basically a huge reverse engineering effort in trying to figure out how living systems work. And so I like this quote because it summarizes the importance of really motion and transport. And so, on the society level, we're all familiar with scenes like this, where there's a highway and there are cars moving around and moving back and forth. And hopefully you'll see an analogy of what happens on the nanoscale. The same logic applies, that you need to shuttle things around as necessary. So this is a long cell, neuron, where a specific cargo has been fluorescently labeled so you can see that it moves around. There's a ton of different cargoes. This is just one type of a cargo. So a cell is an extremely complicated system where you really rely on transport for many, many, many different processes. So we've got a long way to go to really understand how it all works together. But we are certainly making progress on this, and it's really, really interesting. So aside from understanding how transport contributes to the normal functioning of a cell, it's also contributing to the breakdown of cells and thereby to various diseases. So for example, diseases like dementias, right? So you've got diseases like Alzheimer's disease and Parkinson's disease and Fick's disease. In those diseases, transport is broken. We know that, and we know that it's very important to this process. other diseases, developmental diseases, are linked to failure of transport. In many cancers, especially once cells become metastatic, transport is modified. What I want to show you here is an example. Saviz was talking about viruses as they get born. This is when they're fully formed and they're trying to attack a cell. This is a movie of, so these fluorescent dots are individual virus particles attacking an axon. And their life program is to get to the cell they want to infect, get in, and get to the center of the cell so they can replicate. Okay, this is an HSV herpes simplex virus specifically. And basically you'll see that a bunch of them are sitting around, and some of them have already gotten in. And look at those guys. They're just like, hey, go, 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 let's get there. So the way they do that is they hijack normal transport in cells, and they use normal machinery to get to the center of the cell. And so transport, as physicists, as a physicist, I'm very fascinated with understanding this complex matter being living matter. And transport is giving us a window on how it normally functions and how it breaks down. And again, this is why I think it's so fundamental and so exciting. And we know quite a bit by now about how transport works. So there's a method to this madness. Basically, a cell is a highly organized creature, and it's got all these structures, of which I just want to highlight that there are various filaments. Here, there are various filaments which serve as roads for transport. Specifically, there are microtubules which serve as kind of long-distance highways connecting the periphery of the cell with the logical center, although it may not be the geometric center of the cell. And then there are, along the periphery usually, you've got these actin filaments, which are usually shorter and more disorganized filaments, which serve as more of a local roads for transport. Okay. And what I'm interested in studying is the machinery that is associated with the long distance transport, with the microtubules. And here's this is going to be a movie. This is one filament, and it's close up, so it looks big, but it's really a lot of these tiny filaments running all over the cell. And there are molecules which bind to these filaments, and their function is to transport cargoes wherever they need to go. We call them molecular motors. And there's going to be a movie of one of these molecular motors as currently envisioned. Sort of, this is an animation, obviously nobody can see at that resolution, but they did try to capture a lot of the key details. So you can see a lot of these filaments all over the cell, and they're moving the motors are moving the cargoes. And usually when you see pretty movies like this, a lot of the time if they're Hollywood movies, there'll be a lot of fluff, and they'll look pretty, but they'll be fluff. Here they try to actually capture a lot of the key details, and so for example, we do think that these motors move in what's called a hand-over-hand fashion, step by step. And you'll notice, again, they really oversimplified this in a way, because all of these motors are highly regulated. The cell really controls what goes where, and that is happening by other proteins coming in. And so far I've been studying a lot how multiple motors work together, because here you only see one, but in reality there's assemblies of motors that sometimes move cargoes as well. And all of that is very complicated, and we're just beginning to understand how that works. Notice also they've shown one specific motor for which we know a lot. That motor's name is kinesin. There is another group of motors called dyneins, which also bind to microtubules and move in the other direction. We know a lot less about them. And I'm actually very interested in understanding how dyneins specifically work, and then how the assemblies of these motors work together, and how they're all regulated together. And also how the motility is regulated by the tracks on which they move, because if you make an analogy again back to what happens in society, you've got all these signs on the road saying stop or whatever, turn. There are similar regulatory frameworks on the roads themselves, and you can learn a lot about that as well. And so I'm very excited about that side of things. So one of the things that's, okay, next one, okay, good. So one of the things that I'm going to be doing in my lab, which is also highlight a technique, well, this is going to be a cartoon and not a, not a picture of a telescope. But basically, we have this wonderful technique where you can put an individual motor that you've taken out of a cell. It's a nano machine, okay? You can take it out of a cell and it will still work. And you can attach it to a handle, in this case, a glass or a latex bead. And then you can manipulate that handle and you can learn the properties of individual motors or assemblies as you want, whatever you want to study. And the great thing about working with latex beads or glass beads or these kinds of highly refractive objects is that you can capture them using a highly focused laser light. So if you tightly focus your laser light, you can then create what's called an optical trap, where a bead will basically be captured, kind of like a tractor beam in Star Trek, reach in and just manipulate it on a nanoscale. And if the bead is trying to move out of the trap, it will feel a restoring force. And the further it goes, the more restoring force it feels. And so we can manipulate individual molecules by their handles. And for example, we can bring them close to the filaments on which they move, which we can also extract out of cells. And for a while, this bead will diffuse around. And if it diffuses and binds to the filament, we can actually observe that motion and register its properties and study its properties. And here, for example, it kept going farther and farther away until it couldn't apply any more force, couldn't move anymore, sat there for a while, detached and flew back because there's a restoring force. And so we can look at records like that. So I wanted to show you this record, not so much because I'm going to tell you what data you can extract out of it, although you can extract a lot, but I wanted to show you that the scale of the forces that we're measuring to the side is piconewtons. Okay, single piconewtons, and the resolution is a lot better than that. Okay, so we can really study tiny forces with this technique. And if I plot the equivalent of how far the bead actually went in the trap, notice that the scale here has changed into nanometers. We can study stuff on the scale of hundreds of nanometers, but the resolution again is a lot better than that. You can actually see these individual bumps, steps. Remember that cartoon where the motor was going step by step? You're actually seeing individual conformation changes. You can actually see these steps directly in the data. Okay, so to summarize, the focus of my lab is going to be how things are moving on a nanoscale. And I'm going to be using microscopy techniques, and there's going to be some fluorescence, but the core of it is going to be things like optical trapping. And we're also going to be doing a lot of theoretical analysis and simulations, because ultimately the goal of it, like I said, is kind of reverse engineering what's going on. So when you figure out something new is going on, there's a new way of regulating a motor, you want to ask, well, how is it going to integrate it in transport? How am I going to get a new mode of transport? How, where in the cell could this be relevant? And so we're going to be doing that, and the whole point of biology now is moving more quantitative approaches, and we're going to be definitely doing a lot of quantitative simulations of this. And so the lab is just starting in January. So kind of like Sabi's lab is basically empty right now. So if you're interested, shoot me an email. I'm going to be here for the next week, and then I'm coming back obviously soon afterwards anyways, but the next week I'm here, so if people are interested, then we'll probably be doing next week. Thanks.
Okay. Good questions, Michael. Okay, great, thank you, Michael. So, Shanti, by the way, there is a okay.
Don't know my name. So I'm Shanti Dimian, and I'll be here also as of January 1st. I don't have any lab. I mean, I have a lab, but nothing in it, just like the previous two people. So here we have a plot of pressure, range of different pressures, and range of different events that happen in the nature. So as a biological system, I'm not, by the way, a biologist, I'm a condensed matter physicist, but because 2 previous talks were based on biology, I'm going to talk about a little bit of biology. So as a biological system, you're bound in the small region of many interesting events that are happening to you, about 1 atmosphere, and you are going to be living in somewhere in the room temperature. Here are a range of different temperatures and different events that are happening in the world around us. So if you are interested in exploring this region of the phase diagram, you may want to talk to Savizer or Michael or even Jordan. But here are some of the other stuff that are happening. If you go to really, really low pressures, is the interstellar space pressure is 10 to the minus 15 Pascal. And then the lowest obtainable pressure in the lab to the validity of the Wikipedia as of January 2009 is 10 to the minus 11. And here we are. Here is where you about 2 times 10 to the 10, you can synthesize diamond, which is like, I can tell this is valid because it's 200 kilobar. I've done it myself. And then you go to the pressures that you can see in the core of the Earth, which is about 4 million times atmospheric pressure. And then you go to the sun's core, that is like 3 times 10 to the 16 Pascal, and then you can go to much, much higher pressures. And if you're interested in these really, really high pressures, you may want to talk to some of our cosmologists and talking about the supernovas and the core of the stars and everything. Now here in the temperature side, lowest temperature in the lab is 1 times 10 to the minus 12 Kelvin. Here is we are beating the nature because the lowest natural temperature is about 1 Kelvin. Again, from Wikipedia, I thought it was 4 Kelvin, but apparently there is in Boomerang place that this is like this temperature, 1 Kelvin is achieved. Then we're coming to the superfluid helium-4, highest superconducting temperature about 200 Kelvin. This is a room temperature where you're living, and then about 4,000 Kelvin, you can melt the diamond, and you can go to much, much higher temperatures, and if you're interested in those kind of temperatures, you can talk to some of the high energy people. So my lab and my work is basically, I'm interested to start from somewhere around atmospheric pressure and look at the interesting physics that can be found in this region up to the pressures that you can find in the Earth's core. And as you can see, and the temperatures I start, in my group, I would start about the superfluid helium-4 temperature, or maybe, okay, I'm going to say lowest natural temperature, they're not that much difference. And then go up to melting of the temperatures that you can melt the diamond. And there are a number of interesting phenomena that you can see, and I'm going to talk about what kind of physics you can learn here. So basically, this was the region of the temperature that I said I'm going to be, pressure that I'm going to be from here. So atmospheric pressure to here that I'm going to be interested. And then in the lab, you can go from here to here in terms of temperature to much, much higher temperatures. But we're going to start from here to these temperatures. And the questions that we want to answer are questions, so I listed some of the interesting questions that we want to investigate using the pressure and temperature as our quantum control parameters. So we are going to study some of the quantum solids, and I'm going to talk about this one in particular here. And then we are going to look at the quantum phase transition, quantum critical points. Basically, a quantum critical point is that where you are sitting at absolute zero and you're changing another parameter except for temperature, and you're causing a phase transition. And that can happen if you are sitting at zero temperature and you're changing the magnetic field, or you're changing pressure. And here we are using both magnetic field and pressure to see some of the quantum critical points, specifically where you have the superconductor and to the non-superconductor transitions. We're going to be looking for exotic states of matter on the edge of magnetism, and so we are going to look at some of the magnetic system. We are going to use again pressure as a quantum control parameter. We are going to drive the material from one state of magnetic phase to another magnetic phase, and we are going to study what kind of exotic states can be found. And then we are going to be looking at superconductivity, which is a long-standing question, high temperature superconductivity, and we are going to do high pressure synthesis. We're going to try to synthesize materials that are not possible to synthesize at ambient condition in any temperature, and use the high pressure to synthesize this material that can have very interesting properties, and whatever we're going to come up later. Because this is basically the technical tool that we are using to study condensed matter physics. So the quantum solids, this is an example, what I'm going to talk about. So you have a classical solid, you probably heard about the 0-point motion. So if you have a particle, this is the nuclei, and you look at the lattice, these particles are not going to be sitting in the equilibrium place, even if you're at 0 temperature. And they're going to wiggle a little bit by the laws of quantum mechanics around their equilibrium point. And for classical solids, this basically spread of wave function is very small compared to the spacing between the adjacent particles that are sitting in the lattice. For the quantum solids, this 0-point motion is rather large. So basically, the two quantum solids that we know are hydrogen and helium. And helium, this spread and this motion is so large that even at 0 temperature, 0 Kelvin, it never solidifies. So it can't form a solid lattice. In terms of hydrogen, it becomes solid at rather low temperatures. But hydrogen has a very interesting physics behind it. And what happens is that you're starting with a molecular hydrogen. If you look at the solid lattice of hydrogen, we're starting with a molecular hydrogen that is an insulator. Then you start pressing the molecules closer to each other, and you're going to get to the regime. These are all theories. I mean, we are just here in terms of experiments. You're going to get to the regime that basically the electron clouds are going to overlap, and you become a molecular metal. And then if you compress the hydrogen to higher, almost all the theories that are existing are predicting that the molecular bond eventually is going to break, and you're going to have an atomic metal because you have one electron in the S band, just like every other thing in the first column of the periodic table, lithium, sodium, and the others. And this atomic metal, I mean, this is the general picture, but no one exactly knows when this is going to happen, because hydrogen is a quantum solid. So you basically, when you are trying to do theories, you have to treat the nuclei also as a quantum mechanical object. And that's not easily can be done for large stars, for something that, and so no one knows when this is going to happen, when you're going to be getting to the regimes that atomic metallic hydrogen is going to be made. And this atomic metallic hydrogen, by the way, is predicted to have many interesting properties, including that it can be metastable. You know, any of you knows that what is the very good example of a metastable system? The diamond is a metastable system. So basically the form of the stable form of the diamond of carbon at ambient pressure is graphite. So now if you are bringing it to very high pressures and high temperatures, you're going to form a diamond. And you can actually see it in the laboratory condition that we have. And when you are releasing those pressures and temperatures and bring it back to the ambient temperature and pressure, it remains in the diamond form. So basically, I'm going to use the Eugene has a mind. This is for your quiz that we're going to. So basically, if you look at the energies, this is the metastable state. And this is the equilibrium. So basically, this is the stable state. So this is the graphite. This is diamond. When it gets here, if you give a little bit of energy, it's going to get back to a graphite form. So basically, previously, when I was not still an assistant professor, I studied hydrogen as a system to find clues for getting close to the atomic metallic hydrogen. And we had the melting curve of hydrogen. We found the peak in it. That was a great indication of this state to where it's going to happen. So this is kind of the system that we are going to be studying. What technical tool that you're using is a so-called diamond anvil cell. So you are going to be dealing with diamonds a lot if you want to work in the field of high pressure. It's basically, these are two diamonds, two tiny diamonds, they're not very big. This is about 3 millimeters. And you have a metal sheet in between the two. The tips of the two you are going to put a small flat about 100 micron. And this metal sheet is going to allow you to generate a small pressure volume in this right between the two tips of the two diamonds when they're touching. And you can generate pressures as high as the pressures in the core of the Earth. And the size of this diamond cell is something that can be fit in the palm of your hand, and you can get into the pressures in about 6,000 kilometers deep in the core of the Earth. In there. And I was thinking that my lab is like about this, like the major equipment in my lab is going to be 10 to the 7 times smaller than the volume of the lab. So they gave me a very large lab in that sense. So, yeah. But I mean, there are other stuff that do this. This is just very good. That's the tool that major tool that we're using to generate these pressures. You can do all kinds of cool experiments using this diamond anvil cell technique. And here, because all diamonds are transparent and visible and measure parts of infrared, you can do many different kinds of spectroscopy. You can do Raman, IR. You can use the diamonds as an X-ray for doing X-ray spectroscopy. You can do NMR in diamond anvil cell. Here is a coil that I found when I was a grad student many years ago. It's right around the diamond. This is a little diamond, and these are it's like a 3 millimeter cross. And this coil, it was that for magnetic susceptibility measurement that I made. Here is the flat of the diamond. You can put your sample in, and you can put electrical leads inside and do electrical resistivity measurement, and all kinds of different studies that we are going to be interested in my lab. So I will be leaving tomorrow morning, and we'll be back on January 1st. The diamond anvil set that I already ordered is going to be in the lab before I arrive, I guess. And if you are interested in talking about the interesting projects that we that I'm interested in my group, please stop by after January 1st sometime, and I would be happy to discuss things. I can be reached. I don't have a cell phone and no other contact, and I work in my office, so my email would be the best way to find me. Okay, thank you.
Any questions for Shanti?
I missed your last name.
Dinia, that's Jordan's.
No, Shanti.
Mistake.
It's there. We didn't put it out.
Thank you.
Here it is. And I'm going to start working on a website sometime soon. Yep.
I was always under the impression that diamond was kinetically stable. In what sense is it metastable? I mean, there's a huge activation to convert it to graphite, right?
Yeah, well, diamond, if you have carbon and you try to synthesize something at ambient pressure, it's not possible to make diamond, to synthesize diamond. You only have to go to high pressures to form diamond. And if you give a diamond some temperature, like if you put it in a safe box and the place that you are gets on fire, the diamond is going to evaporate, and it's not going to form diamond again. It's going to form graphite. So, yeah, it's metastable. Yeah.
Is there enough reason to know that to change the hydrogen into an atomic metal, that it's within the capability of diamond? I mean, you're pressing on the diamond as well, right?
Yes.
How do we know the diamond will survive this before the hydrogen? Is there?
Well, the pressures that you can get inside the diamond anvil cell in the laboratory environment has been to about 5 million times atmosphere. Already at 3 million atmosphere, there has been indication that hydrogen was becoming black, which is not a proof that it's becoming. It's like the gap is closing, so you're getting to the close to the metallic phase. And if you extrapolate those data, it's about 4 megabar. You can get to the place that the hydrogen becomes metallic. But the problem is that it's very difficult to confine hydrogen inside diamond cell because it diffuses out of the cell. It's just so small.
Okay, we better move on. Thank you. Okay. That's your time. We move on.
came in here when Saviz was starting his talk, and I've decided that what I'm going to do is take a sabbatical next year and work in any of the 3 labs that the talks. So I'm just, who would not want to work on that stuff? It's really, really cool. And I will tell you, students, that it's really awesome to you think it's going to be a lot of work, and it is, but it's very rewarding to start in a lab that's empty with an advisor and build stuff and really see it come together and put it, and then start doing experiments. It's really awesome. Now, that doesn't apply to me because I've been here for 10 years. And our group studies these things called, I also wanted to thank Jordan for scheduling my talk at halftime of the Michigan-Wisconsin game. Because, so now I can do this. And all right, so anyway, what do you do? Hyperpolarized gases. So I'm going to tell you a little bit about these things. We do a bunch of stuff. The main theme are these things that I'll call hyperpolarized gases, hyperpolarized noble gases. And what we're doing is we're polarizing, we're aligning the spin in the nuclei of noble gases, principally helium-3 and xenon-129. And, some pictures here. Let's see. Which?
The red one.
The red one? Yeah, this one. Okay. So I'll tell you about, we make xenon, hyperpolarized xenon. I'll show you, I'm going to explain what this is all about. I'm just going to move on and sort of talk. So we're dealing with nuclear magnetic resonance, and that's a prime technique that we use in the laboratory. So if you want to know what that is, here's some stuff. Stuff has atoms. Atoms have nuclei. Nuclei, many of them have spin. All right, now quantum mechanically, we have a magnetic moment associated with that that's proportional to the spin I by gyromagnetic ratio gamma. There's a Hamiltonian called the Zeeman Hamiltonian that is mu dot B. That's where the energy of the spin comes from in the magnetic field. And of course, there for a spin 1/2 is the simplest, right? It's either up or down with respect to the magnetic field. So there's an energy separation that looks like h bar times omega L. Omega L is called the Larmor frequency, and it's proportional to the applied magnetic field. It's typically tens of megahertz in laboratory fields. So think FM radio, and you got it, all right? That and kind of higher. So if I model it this way, here are my spins, my nuclear spins, and they've got 2 possible energy states. It turns out that in sort of classical NMR is well over 50 years old. And in sort of conventional classical NMR, what you work with is a thermal equilibrium distribution of the difference between these 2 populations. So in other words, if I handed you 1,000,000 pairs of spins, in a typical laboratory magnetic field, one such pair would have both spins in the low energy state, sort of point oriented in one direction. So you live with polarizations, if you just define it as the number of ups minus the number of downs divided by the total number. You live with polarizations that are on the order of the energy, mu b, the moment times magnetic field, divided by kT. And that turns out to be small, okay? And then, of course, there's also another interesting property of this system is that a time that we call T1, a relaxation time. So if I just throw a sample into a large magnetic field and I ask how long does it take to establish this equilibrium, that time is called T1, okay? So that's sort of NMR 101. The way we see a signal is, in a sample like this, is we'll apply a resonant RF pulse at the Larmor frequency that'll mutate the spins away from the applied magnetic field, and then they precess. Okay, the transverse component of that mutated magnetization precesses rapidly around the magnetic field, and then you have a pair of pickup coils. It's just Faraday induction, okay? It's just a pair of pickup coils that picks up this signal, and you read it out. You say, man, these are tiny things, and they got a small moment, but in a typical liquid sample, there's 10 to the 22 spins per cc, so you got a lot of them, all right? And they add up, and you can generate a signal, provided you have some sort of polarization. So in our lab, we do typically what I call cheating thermodynamics, where, if you look at a thermally polarized proton sample, that's what I just discussed. High density, low polarization. So 10 to the 22, typically 1 in a million, maybe 1 in 100,000 if you have a particularly big magnetic field. Hyperpolarized noble gases that I'll talk about, if it's a gas, you're typically dealing with densities that are 3 orders of magnitude smaller than liquids or solids, but what I'll tell you about is a technique that we generate polarizations that are on the order of 10%. So instead of 1 in a million pairs, 1 in 10 pairs, 1 in 5, 1 in 3, something like that. And these Hyperpolarized gases are going to make a wide variety of magnetic resonance experiments with gases much more sensitive and feasible. And of course, the other question you always want to ask is, do you care that you can make polarized gases? And it turns out you probably should. Okay? So what is this process that I'm talking about? This is called spin exchange optical pumping. So I am an experimental atomic physicist by training, and so we do a lot of experimental atomic physics, and this is where it starts. We are interested in angular momentum capacitance, if you want to think of it that way. We start out with angular momentum in circularly polarized light. You remember that carries h bar per photon. There's this process called optical pumping, where we polarize the valence electrons of rubidium atoms. Remember, these things are alkali. We make alkaline metals. We make a vapor out of them. They have that one lonely electron that hangs way outside the last closed shell. This is the interaction we're talking about. Then those polarized electrons, now think of this all taking place in a glass cell, where the laser is shining on the glass cell. Those polarized valence electrons interact then with our noble gas atoms, helium-3 or xenon-129. And that electron is hanging out so far away from the rubidium that there's some probability in a collision that it will overlap the nucleus of the noble gas, and you'll have what's called a zero quantum transition, if you want, or a mutual spin flip. The polarized rubidium comes in, flips the nucleus of the noble gas, and then flies away. But wait, the laser's still on. So the rubidium flips back up, finds another noble gas atom. This happens again. And slowly but surely, the angular momentum that started in the light made its way through the electrons of the rubidium and now finds its way into the nucleus of the noble gas. And it turns out that it's stuck there, mostly. Okay? So one of the things we study is how it leaks back out. But those times are typically very long. Now, spin exchange itself, so here's a schematic showing you how this works. 40-watt laser, yeah, this slide's a little bit old, so we're up to 60, 80, even 100-watt solid-state lasers. These things are amazing. When I was in graduate school, we had titanium sapphire lasers, a room full of equipment, a couple $100,000, 50 kilowatts out of the wall, and you got like 3 watts. And now these things have a footprint about that big. They cost about $1,000, and they kick out 100 watts. And they're really more like photon fire hoses than lasers, okay? And you just, you don't want to get in their way. But for us, all we care about is the photons. We care about getting photons at a specific frequency. All right, so I want to tell you a little bit about what our lab is doing now. You come up and talk to me about the physics of optical pumping, how that light is transferred to the electron and then transferred to the nucleus. But essentially, that's what this is showing. We've got some optics, some collimating optics, an oven. The beautiful thing about the oven is that you raise the temperature, the rubidium comes into vapor, so it's a saturated vapor pressure of the alkali, it absorbs the light, and it transfers the spin from the rubidium to the, say, xenon here. And then when you're done, and this process takes tens of minutes for xenon and can take hours for helium. It's a very long process by any atomic physics standards. Cross-section is low, and it only happens during collisions. Okay, but then you can lower the temperature of the oven, take the rubidium out of the vapor, it plates to the walls of this little glass cell, and again you have this polarized sample of gas that's just kind of stuck in that state, and then you get to play with it. Okay? So how do we play with it? Well, there's a bunch of ways to play with it. I'm showing a few things here. Probably the one that gets the most press is if you polarize helium-3 to 70 or 80%, you can have somebody breathe it. And if you have somebody breathe it, well, you can do MRI in their lung. So this is actually not a human lung, it's a guinea pig lung, but it's been done in humans too. And the beautiful thing here, of course, is that, in a healthy person, there's no water in your lungs, so the natural MRI signal from that water, that thermally polarized water, is non-existing. This allows the possibility to image the lung with MRI and also to watch gas move through the lung. That's the function of the lung, so it's actually a very, potentially very useful technique. This is also used sort of in a biochemistry sense. People are playing with xenon and trying to do sort of molecular imaging by linking it to some ligand that has a target and then having the xenon, which again is hyperpolarized, light up where it's bound. And then there's also some very fundamental physics that's done, searches for electric dipole moments and this sort of business, which is my colleague Michael Moss at Princeton. So very fundamental sort of search for what I call physics beyond the standard model, PBSM, right? These applications all rely on high polarization and long lifetime for these gases. and they rely on a thorough understanding of the physics that produces them, and that's in large part what we do in our lab. So think of it like filling a bucket. I'm trying to fill a bucket with highly polarized, say, xenon, and one of the things that happens is the bucket leaks. Those are these relaxation mechanisms. So I cool the cell down, and the angular momentum is stuck in the nucleus, but guess what? It leaks out. It leaks out by colliding with other atoms, dipole-dipole type interactions. It leaks out by colliding with the walls of the vessel. And so I'm interested in these interactions and these leaks. I use NMR to measure the polarization and also to measure the leaks. Okay? And I won't go into this too much, but the idea is that I'm always comparing a spin exchange rate, how fast does the angular momentum get transferred into the nucleus, to the sum of a spin exchange rate and some sort of auto-destruction or a wall, some kind of wall relaxation rate or a general relaxation rate here in the denominator. Our goal is generally to understand it and minimize this relaxation so we have the largest possible polarization, and then we can produce it in the shortest amount of time. Okay? So let me just show you some data. Now, I'm going to try to tell you a little bit, and obviously it's 10-minute talk, so it's kind of fast, but we can talk about it later if you want. This is really pretty remarkable. I know it doesn't seem like that to you because if you've been in the field for 20 years, you realize that a 100-hour gas phase T1 for xenon-129 is absolutely stunning. Okay, so typically for the longest time, gas phase relaxations were in the minutes or tens of minutes, maybe an hour. And most recently, we got this data. Oh, by the way, I used to show data like this. This is measuring an NMR signal as a function of time. Now look at the scale here, hours. Okay? I used to show data like this, 10 years ago, not this long. But I would show these measurements of T1, and there'd be these big gaps in the data. And I'd always make the joke that, well, the graduate student decided he really had to sleep. Okay, so now, of course, the graduate student sets up the computer to acquire all this automatically, right? And so now there's no gaps, all right? So this is a 100-hour T1. This is important because this was an indication that we understood a very important relaxation mechanism in xenon, which is that xenon makes molecules. It makes dimers with itself. And so you got a 1 atmosphere sample of xenon. It turns out 1% of those atoms are bound in van der Waals molecules, and that dominates the intrinsic gas phase relaxation. So this was work by a graduate student, Ben Hanger, who's now a postdoc at Leiden. This is another big chunk of work we've done, and my student Jeff Schrank just graduated and is doing a postdoc up at Pacific Northwest National Laboratory. He actually built and designed this thing. This is what we call a flow-through xenon polarizer. Xenon has, under some conditions, really fast spin exchange rates, and so we built a device where the xenon flows through up the long, meter-long cell that is kind of hard to see, but it's here. This is looking down from the top on this cell. The laser actually goes down from the top while the gas is flowing up, and in a couple of minutes' time that it takes the gas to flow up to the top of the cell, it gets polarized, and then it comes out, and then we can freeze it and separate it, and we can keep it around for a few hours, or we can store it, or we can conduct it directly to an experiment. So I call this kind of xenon on tap. And we're taking the best knowledge that we have of all the physics of spin exchange optical pumping and combining it into this device so that we can produce about 10 milliliters per minute of xenon polarized to about 20%. If you lower the flow rate, you can about double that polarization. Okay? What else? Well, we freeze the xenon after we make it. Lately, I have to say, I've been doing a lot of xenon work. And the reason is that helium-3 is now being confiscated by the government to do neutron detection at ports. And so it's hard to buy. And if you do buy it, it's like $2,000 a liter. So for that and other reasons, I've switched a lot of my focus recently to doing work with xenon. So I call this extreme signal to noise, NMR, where we hyperpolarize xenon to 10%. We freeze it as a polycrystalline solid. We actually use xenon that's enriched in xenon-129, so naturally abundant, it's only about a quarter. We enrich it to about 90%. And then we take and we make a solid out of it. So now it's got both things, right? It's got the hyperpolarization, and it's dense like a solid or a liquid. And on top of that, I'm going to apply the maximum pulse I can to it to get the biggest signal. And then I say, get a fire extinguisher for your NMR preamp, because it's big. It's a big NMR signal. Now, that's, I don't know, it's like kind of saying like a big mouse, all right? Because NMR is weak, right? Nuclear moments are intrinsically weak. But these are some really big NMR signals, and what you can see is that we're watching, this is a log scale now, we're watching the transverse magnetization decay with time. And These beats have a lot of very curious physics in them, but look, this decay happens over about 4 orders of magnitude, where we have pretty decent signal to noise. It's a big, big signal. And we're actually very interested in the late time of this decay and its potential relationship to the interface between quantum mechanics and chaos. And that's all I'll say about that, because it's at least another hour to talk that through. Another project I'm doing, I should point out, 2 of my graduate students are in the audience here. Eric Sorty is back there. He's your GSAC chair, right? And then Zaid Ma, who's right in front of him. And Eric is working on the solid xenon stuff. And Zaid has been working on this chemical shift interaction between xenon and protein. So we have a collaboration with Dave Goldenberg in biology. And we're looking at this model membrane protein called BPTI. And we're studying xenon binding to this protein and trying to get a handle on how its chemical shift is related to this binding. So let me explain. NMR frequencies depend on the chemical environment that the xenon finds itself in. And so it shifts the frequency ever so slightly if it's bound. And so this data is indicating, as a function of protein concentration, this shift in the xenon resonance frequency for a wild type, that's the black, and for a bunch of mutants. And there's some reasons here as to why some of these slopes are really shallow and some of them are quite steep. If all the binding affinities were the same for all these different kinds of mutants, then the steeper slopes would be an indication of relative, if all the binding affinities are the same, it's an indication of what?
Would they have the same
All the
slope?
shifts are the same.
All the shifts are the same. If all the shifts are the same, thank you, Dave. If all the shifts are the same, if the chemical shift is the same, then these slopes would be an indication of relative binding affinity. And we're working right now to sort of separate those 2 out. So a tiny little bit of biophysics. Right now, this is at the stage more of technique than of doing real biology. But this data is taken with extremely low xenon concentrations in the protein solution. And the reason we're able to get it is because we have a really stable magnetic field and because we're hyperpolarizing the xenon, so we have a really big sensitivity. So let me just end or summarize by telling you about some current projects that we have in my lab. The development of hyperpolarized xenon production apparatus, what we call our polarizer, or flow-through polarizer, and the associated spin exchange physics. Our quantum mechanics books are dog-eared and coffee-stained. Okay, you're going to learn some quantum mechanics, some spin physics, all right? It's really cool. If you like that sort of thing, it's a good lab to be in. Long-time behavior of transverse NMR decays in frozen hyperpolarized xenon. That's Eric's project I talked about very briefly. This xenon protein binding studied through the xenon chemical shift. Let me mention a couple of things that are kind of new on the horizon. One is that we're going to try to use some helium-3 MRI to investigate alligator lungs. Alligator lungs turn out to be weird in the animal kingdom. Actually, it's bird lungs that are weird. Studying the lung of alligators, though, is kind of like studying birds, and we're teaming with an evolutionary biologist, and this has implications for how the relationship between reptiles and birds evolutionarily. Okay, so that's on the rise. And then another one with my colleague here, Valerie Bardini, who's right there in the vest. We've just started working on organic spin valves. This is preliminary. Valley's the world expert in this. And he just kind of had this idea and came to us about using NMR to study a process by which polarized electrons are injected into an organic material, and it's believed, it's suspected, that they lose their polarization to the nuclei in the material. If that happens, we ought to be able to see those polarized nuclei with NMR. Okay? So I have Eric working on that, as well as an undergraduate in my lab, who's an Access student, Laurel Hales, who's working on this. And in fact, they called me yesterday, or Eric called me yesterday, because we finally saw a signal from this material, and we're going to be able to do some preliminary NMR measurements of T1 and T2, go down to cold temperatures where we really need to do the experiment. So that's kind of taking off now, too. And that's all I have. Thank you very much for
Okay, so we're well behind time, but we are going to take a break. So let's take a 15-minute break, and if you want to ask Brian questions, let's do it out over coffee and cookies. Okay? Thanks.